a surge that is taking place from this point. So the only allowable variation of m dot is such small at high rotational speed. You see very small variation, and we see that here very clearly already at m dot L you have the problem. Whereas when you are at low rotational speed, you need to go to a much larger variation of the rotation of the mass flow rate, and you have a problem in the first stages, where you have h that is high, and you may have there a position of rotating stall. Of course, if you increase the problem, so if you go down more and more in m dot L, then you will go to the surge. And we see that also very clearly on the compressor map, because if you take this curve, which is at a much lower rotational speed here, you see that the variation you need to have in delta m dot, allowable, before going to surge, is much larger than here, much larger than there. So it's very, very clear. And so we see that when analyzing a compressor multi-stage, it's leading us to this explanation showing that depending on the rotational speed, you will have a different problem when you look at the, let's say, left-hand part of the graph. When you will be at high rotational speed, you will go most probably directly into a surge problem, no rotating stall possible, whereas at low rotational speed, you may have first a problem of rotating stall, and then a further decrease of m dot can give you only after a certain further variation of m dot the problem of surge. So the rotating stall is possible, but only at rather low rotational speed. Low rotational speed, the lowest, this is something like 66%. It's not zero, because the first stable point of an engine is around 60, 65, 66, it's 2/3%. So when I say low, this is at 65%, at 70%, at 75%, maybe at 80% you can have rotating stalls points, but not in the region of 90, 100, 105% of the nominal rotational speed. Very, very interesting. So the situation that we can explain thanks to, let's say, a stupid rationale as the one that we have shown here. Of course, surge we don't like. We must avoid surge. This is dangerous. I explained yesterday at the end of the lesson. For the temperature you can have in the turbine, you can burn the turbine. It's dangerous because you can blow out the flame in the combustion chamber, and then you will have to reignite your combustion chamber and your engine. We will discuss about that later on. It's difficult. But also, I explained to you that you could have even an inversion of the flow, and that the flame could flow through the engine. But the first stage here, the fan is maybe in carbon. So if you have a flame going there, the carbon, it will remain nothing of the carbon blades after that you have had the flame going through the front, of course. So surge is to be avoided, let's say, at all times. At all times. This is something that cannot be a load that is not affordable. Absolutely not affordable. So you need to find solutions. So what are the solutions? First, you can try to play with the velocity triangles. So we have seen that we have our blade. This is the reference direction of our blade. This is the chord. And we have the angle of attack. The angle of attack, I'm increasing the velocity triangle. This is related to the absolute velocity that I represent as axial, because this is the first stage of the rotor, so normally the velocity is axial, if there is nothing special, no side wind or something like that. This is, so axial, huh? This is U, and this is W. And this is the angle of attack, and let's say that we are at the angle of attack max. If we go 0.1 degree above, hop, the problem is there, catastrophic situation. How can you decrease the angle of attack? I will exaggerate the situation, but let's say that you put the velocity vector like this. Of course, with the same axial speed, because the mass flow rate is in my rational constant. Huh? So if you change not the mass flow rate, but just the direction of the mass flow rate, so V is becoming this direction, U is still the same, so U is now between this point and this point, so maybe even like this. This is the new, this is the same U, but starting from this point, you see that W is now this direction, W is this direction. If you take the same direction of the chord, you see that the angle of attack is this one, much smaller than the angle of attack that you have there. So if you change the direction of the absolute velocity, this is gained. And how can you do that? You can put here in front, there are different solutions. You can put a blade that is symmetric, like this, and that can rotate. So normally this blade is axial, this is the normal condition, and if you rotate this blade like this, so it's symmetric, it's not so easy to draw, it's a symmetric blade. If you draw the blade like this, you see that you will put the absolute vector in this direction. And so you just need to rotate the blade. There are some blades that are, let's say, like this, and where it's only the rear part that is rotatable. So it's only this part that can rotate like this, going from this direction to this direction. It doesn't matter. This is what is called variable inlet guide vanes. So these are guide vanes that are variable in direction, but this is a blade, of course, that is not existing, because a compressor, this is starting, you put this blade here. You put this blade here, and it must be orientable, like this. So you need to introduce variable geometry, and you introduce a new blade. This is weight, this is pressure losses, this is a lot of problems, maintenance, etc., etc. You can do that also for this blade. You can do that also for the second rotor, the second stator. Then they are more calling that variable stator vanes. Here they are calling that variable inlet guide vanes. Here they are more calling that variable stator vanes. And of course, it's solving the problem, but it's increasing the weight, increasing the complexity. All the blades, they must rotate with the same angle, etc., etc. This is a problem. You can have all stator blades moving like this. And this was the problem of, who has invented the first axial compressors? These are the Germans during the Second World War. But in fact, they had not variable geometry. They had compressors without this possibility. No variable inlet guide vanes, no variable stator vanes. Everything was fixed. And as soon as they were, let's say, decreasing the rating of the engine, as soon as they were doing maneuvers where they need to have extra power, in fact, they were surging the engines. And that's why on the Messerschmitt 262, they had so many problems with their engines. They were good, they were fast, but their engines were not adapted because there was no variable geometry. And these are the Americans who invented the first axial compressors with variable geometry. So it has been invented by General Electric after the Second World War, and hopefully the Russians had not this technology, because they had, let's say, a very good engine, but not so good, because their axial compressors were suffering a huge problem of surge, to the benefit, of course, of the allies and of our populations. Okay? Also, there is something else that we must mention. We are facing a huge problem when we start the engine. Because when you start the engine from 0. Rotational speed is 0. So you will need to go through the low rotational speeds, and you will need to go through low m dot. Because you start your engine from n is equal to 0, and m dot is equal to 0. So, and first you have 1 gram per second, 10 gram per second, 100 gram per second, 1 kilo per second, etc., etc. So you are facing this problem. There is no way to avoid having low rotational speed and or low m dot. So how are you starting the engine? Because if everywhere in the world the engines are what we have explained until now, it will not work. So what will you do? When you start the engine, so at engine start, the n is small. When n is small, where is the danger? In the first stages. Only in the first stages, not here. So you have to solve the problem only in the first stages. So, and in the first stages, only in the first stages, what do you need to do? You need to increase m dot. If you increase m dot in the first stages, even at low n, you will not have the problem. And how can you solve this? You will make a hole here. A hole, this is of course a band like this. This is like a belt on your pant. A belt. You are opening a belt, so it's making a hole over 360 degrees. And like this, you have less overpressure here than there. And so you will have a part of the air going there and a part of the air going here. Let's say 1, 1. And like this, here you have 2. And so, like this, you solve the problem at low rotational speed of starting the engine. When the engine is started, you close this. This is what is called a bleed strap. Bleed strap, bleed belt, you could have called that, and you close that when the engine is started. And like this, you avoid the problem. Of course, this is only used at low condition when you start the system. But in fact, like this, you are introducing variable geometry. This is not a good solution. So the manufacturers, they try to find other solutions. They cannot solve all the problems with non-variable geometry. But what will they do? They will also do one thing. The blade that we have taken, this is, let's say, a long blade like this one, with a certain H and a certain C. What will they do? They will